Good morning, students. In this session, we are going to discuss about the topic hydrogen bonding. What do you mean by hydrogen bonding? Hydrogen bonding is nothing but it's a type of bonding exists between a highly electronegative atom and a hydrogen atom. Let us get in detail regarding the hydrogen bonding. Okay, before that, we should know some basic concepts regarding the electronegativity. What is the meaning of electronegativity? Electronegativity of an atom or ion is its ability to pull electron towards itself in a covalent bond. The most electronegative atoms are found towards the top right of the periodic table. That is group 7. That includes fluorine, chlorine, bromine, iodine and astatine. As the electronegativity increases, the strength of hydrogen bonding increases. So, in general, electronegativity plays a vital role in deciding the strength of hydrogen bonding. Right. Among the periodic table, fluorine is the number one element, exhibits a maximum intensity of electronegativity. The basic reason behind this is effective nuclear charge and smaller size. Okay, here we list out the electronegativity values of halogens as well as some other p block elements. If you have a close look on the electronegativity value, fluorine is the one predominantly exhibit more electronegative value when compared with the remaining halogens. And the nitrogen and bromine is almost closer to each other. But though the electronegativity is same, the tendency to form a strong hydrogen bonding is more in nitrogen than bromine. And the reason is nitrogen is smaller in size when compared with bromine. Hence, the density of electron is more in nitrogen. Hydrogen bonding. There are three types of bonds which give a molecule significant hydrogen bonding. NH, OH and FH. This NH type is normally exist in amine related compounds and OHs normally exist in alcohols as well as aldehydes and carboxylic acids. FH is nothing but halogen related compounds. These three bonds all have a strong permanent dipole, hydrogen atom, an atom with a lone pair electrons. What is the meaning of dipole? Dipole is nothing but separation of two charges by a distance d. How the electronegative value decides the permanent dipole character? As the value of effective nuclear charge is more, electronegativity character is more. As the electronegativity character is more, then the dipole formation is more. Hence, these atoms, nitrogen, oxygen and fluorine, is found to exhibit more hydrogen bonding when compared with the remaining atoms. Here, we plotted the boiling point correlated with hydrogen bonding. In what aspect hydrogen bonding and boiling point correlate with each other? Okay. In general, as the strength of hydrogen bonding increases, boiling point increases. Let us have some few examples to have a clear idea regarding the boiling points. Methane, tetrahydrosilane, tetrahydrogermanium and tetrahydrogen. So, among this, the tin tetrahydride is found to have a higher boiling point when compared with carbon. In the similar case, water, hydrogen sulfide, hydrogen selenide, hydrogen telluride. In this, the water is found to have a higher boiling point when compared with the remaining material. The concept behind this is, here the hydrogen is common in all the cases, only the central atom varies. The central atom in general should exhibit a more electronegativity to exhibit a high hydrogen bonding. So among all the elements, the oxygen is the element having a more electronegativity character. Hence, the hydrogen bond formed by the water molecule is more stronger when compared with selenium. Okay. Since sulfur is less electronegative than oxygen, it does not exhibit that much efficient hydrogen bonding. That is why hydrogen sulfide exists in a gaseous state, whereas water molecule exists in a liquid state. Next. Okay. Just now we discussed that there is a hydrogen bonding exists between our water molecules. This hydrogen bonding in water molecule results in some unusual properties. Number 1, higher than expected boiling point. Number 2, high specific heat capacity. Number 3, ice is less dense than water. Okay, let us have a few discussions regarding one by one. why the boiling point of water is higher. In general, the boiling point of water is 100 degree. Why it is 100 degree? The reason is the energy required to break the intermolecular hydrogen bonding is equal to 100 degree. If you supply that much amount of energy, then only the hydrogen bonding get cleaves and it get converted to the gaseous state. Number 2, high specific heat capacity. Okay, it means it absorbs a lot of heat energy with only a small change in temperature. And again, the reason behind this is hydrogen bonding. So sufficient amount of heat energy is required to raise the temperature to a marginal level because of the stronger intermolecular hydrogen bonding. Number 3, ice is less dense than water. Again, the fact behind this is inside the ice molecule itself, there is an interlocking hydrogen bonding. Because of that reason, it is more less dense than water and it creates some volume behind, hollow volume behind that. Okay. Just have a look on this picture. You can able to find some dense close pack arrangement at the right hand side, whereas on the left hand side the density is quite less. Okay, and the left hand part is nothing but it's a section of water in a frozen state, and this is a section of water in a liquid state. See, if you closely look at the structure, the density is more in water when compared with the ice. That is why ice gets floats on water. Okay. Here, the ice structure is a large empty spaces, which gives it a lower density than water. Because of the voluminous, the ice get floats on the surface of water. Now let us have a clear discussion regarding the hydrogen bonding in the molecular level. Hydrogen bonding in hydrogen fluorides. Between hydrogen and fluorine, fluorine is more electronegative than hydrogen. Because of this, it having a tendency to form a hydrogen bonding like this as shown in the figure. Here the fluorine from first molecule is get involved in the hydrogen bonding with the hydrogen of the second HF. Similarly, the fluorine atom of the second HF is get involved in the hydrogen bonding of the third hydrogen fluoride, and it's keep on connecting through intermolecular hydrogen bonding. Because of more electronegativity value of fluorine, the hydrogen has acquired a more electropositive character. Because of this more electropositive character, it gets involved strongly in hydrogen bonding. Normally, the hydrogen bonding is represented by a dotted line. The reason behind this is, when compared with the covalent bond, the strength of hydrogen bond is weak. In order to represent that weakness, we are representing in a dotted line. Okay. This is the structure of ice. This is how the water molecule in ice get coordinated with the another 4 water molecules. See here, the black dot indicates the hydrogen atoms and the dotted line indicates the hydrogen bonding. So one water molecule is having a tendency to form hydrogen bonding with 4 other water molecules. Hence the coordination number of ice in a water molecule is 4. The coordination number indicates a number of water molecule gets surrounded by a single water molecules. Here we given some physical properties regarding the strength of hydrogen bonds and covalent bonds. Now, if you closely look at the values of covalent bond, for example OH, that is alcoholic OH, the value is positive plus 464. The positive sign indicates it's an exothermic reaction. We have to supply this much amount of energy to break the covalent bond between oxygen and hydrogen. Similarly, if you closely look at the structure of hydrogen bond, the energy required is 10 to 40 kilojoule. So when compared with the covalent bond, the energy required to break the hydrogen bond is quite lesser. Okay, instantaneous dipole-induced dipole. The attractive force between dipole and induced dipole force is almost equal to 10 degree or less than 10 degree. So this is still lesser energy is required to break the dipole-induced dipole force of attraction. How do these molecules differ in boiling point, viscosity and water solubility? Okay. Now, for instance, we consider 2 compounds, propane and ethanol. Almost both the molecule are having a comparable molecular mass. In general, as the molecular weight increases, van der Waals force of attraction increases and hence boiling point increases. But here, the van der Waals force of attraction is not the same, but the molecular weight is close to each other. The only difference is in ethanol, we are having a alcoholic group. That alcoholic group is responsible for the strong intermolecular hydrogen bonding. Hence, alcohol is having a more boiling point when compared with propane. Now, let us consider about the physical properties of some alcohols. Alcohols molecule can form hydrogen bond to each other to water molecules. And this is due to the solubility in water. See, if you closely look at the structure, the alcoholic hydrogen is having a tendency to form hydrogen bonding with the water as well as the alcohol. Hence, the solubility is more in alcohol. Results of hydrogen bonding. Wool and nylon fibers can hydrogen bond to water, but these fabrics can absorb water. Polythene has no hydrogen bonding because in polythene there is no more electronegative atom. Hence, the concept of hydrogen bonding is not provided there. Okay. And ice floats on water, making life possible. So, okay. Next topic is types of hydrogen bonding. Hydrogen bonding are categorized into two types: intermolecular hydrogen bonding and intramolecular hydrogen bonding. What's the difference between intermolecular and intramolecular? Let us have a look at the intermolecular. If there is a hydrogen bonding exists between two molecules having a more electronegative as well as electropositive element, that we used to call as an intermolecular hydrogen bonding. Intramolecular, within a molecule, if there is a more electronegative and less electropositive element is there, then there will exist an intramolecular hydrogen bonding. In general, intermolecular hydrogen bond is stronger than van der Waals force of attraction. Here we provided a few more examples regarding the intermolecular and intramolecular hydrogen bonding. Number 1, orthonitrophenol. If you closely look at the structure of orthonitrophenol, the oxygen atom of nitro group is getting involved in the hydrogen bonding with the alcoholic OH located at the ortho position. Similarly, if you closely look at the structure of paranitrophenol, the hydrogen of phenolic group get involved in the hydrogen bonding with the oxygen of nitro group of second molecules, and this is known as intermolecular hydrogen bonding. Between these two molecules, the boiling points is 215 degrees Celsius for the orthonitrophenol and the melting point is equal to 44 degrees Celsius. Whereas for intermolecular hydrogen bonding, the melting point is 113 degrees Celsius. This huge difference in melting point is due to the presence of intermolecular, because in order to break the intermolecular hydrogen bonding, the energy equal to 113 degree has to be provided to break it and make it as a discrete molecules. Similarly, if you closely look at the structure of acetic acid, in general, acetic acid exists in the form of dimer. Dimer is nothing but it's a interlocking between the two acetic acid through hydrogen bonding. And there is even metanitrophenol also having a tendency to form intermolecular hydrogen bonding. Here, the OH group of one nitrophenol is getting involved in the OH group of nitro unit of other nitrophenol. Similarly, boric acid. Even boric acid also exists in the form of dimer through the intermolecular hydrogen bonding. Okay, many organic acids can form dimers, but due to hydrogen bonding, and certain organic molecules can also form an intramolecular hydrogen bonding. Just before we had a discussion regarding the nitrophenol. Similarly, even ortho-hydroxybenzoic acid also exhibit the same intermolecular hydrogen bonding. Thank you.